Swayam Prabha. Digital India. Educated India.
So, students, we are going to discuss further on matenzetic transformations little bit before I move on to the transformation kinetics. So, as you know, matenzites are very classical features of steels. So, that is why the discussion of detailed nature required. Matenzites looks like a distorted plates or laths in the microstructure. But why do they get distorted and how the morphology actually develops, that requires little more discussion. As we have seen that any steel, once it is quenched from the high temperature, it forms matenzetic plates, and these plates, they are arranged in any direction on the microstructure. That is what is observed in the optical as well as SEM microstructures. Now, we can actually see that they actually indeed looks like a plates, that is what I have shown you earlier also, and they are faulted, and basically faults lies both inside the plates as well as on the surfaces, that is along the plane between the austenite and the martensites. But mostly internal faults are more predominant in the microstructure, that is what I have shown you. Internal faults like twins are very predominant in the matenzetic plates. Now, I came to know that these things can be easily discussed using a nice analogy, and that analogy is there in the book of Professor A.K. Jena and Professor M.C. Chaturvedi, and I am taking directly the example from this book. As you clearly see that before the transformation of martensites, there are some scratches made on the surface, and then the steel was heated to high temperature and quenched in water. So, obviously martensitic plates will form on the surface, and this normally creates surface relief. That means the distorted plane comes out from the surface and creates a surface relief. That is what is seen there. You can see there is a distorted region along these lines. Let me just show it. Okay. Anyway, so this is the distorted plane as you see here on this along these directions. Now, one can actually look at the scratch. The scratches were actually moving on the plane of the parent phase austenite, then it gets bent on the martensitic plates, then subsequently they again remain flat on the surface. So, we can represent this whole situation in a schematic manner. That is what I am showing on these like a distorted plates. The MNOP is the undistorted plane of the austenite before the transformation, and EFGHIJKL, that basically is the distorted martensitic plates. As you clearly see, the scratches were moving on the flat MNOP surface, then they get bent. As you clearly see, it was moving like that, then it get bent along BC, okay, and then again moved out from these distorted martensitic plates. So, therefore, but the scratch was continuous, it has never been displaced from the parent to the martensitic plates, it was continuous. That means what? That means both the martensitic plates and the parent austenitic phase has a definite crystallographic orientation relationships, as well as they are maintaining the planes like EFIJ and LK or GHLK, these planes which were in actually parallel to the parent austenite, they are maintaining those two planes same. And it is very evident from these two planes, that is EFIJ and GHLK, they are the ones which are actually habit planes, because they have not undergone any kind of a distortion. Okay, distortion happens along on the planes of EFGH and IJILK, the bottom and the top planes which has got distorted, they got bent basically. On the other hand, the planes which are lying on the sides of these plates, those are in contact with the austenite, parent austenite, they remain undistorted. So, it is very interesting situations, because the shape of the martensite is mainly because of the distortion, very clear. Martensite forms plates or the layers because of the distortion, and this distortion is happening only along certain planes. The planes which are remain attached or remain parallel to the austenite, they are actually not getting distorted. Okay, so it is very evident if I plot or if we actually calculate using tools the strain levels or strain actually induced both in the martensitic plates as well as in the austenites, and can be plotted like that. As you see, A stands for austenite and this is the martensitic plate inside it. As very clear, the strain in the martensitic plates, you can see here, this is on the AB line, it remains flat before distortion or before formation of martensites. After formation of martensites, this getting is elastically distorted in the austenite on the both sides, and inside the martensitic elliptical martensitic plates there is a huge parallel distortion, and this leads to surface relief. One of the plane become bent, and that causes surface relief. It is evident that strain inside the martensitic plate is very large, that is obvious from this picture also, but there are sufficient amount of elastic strain in the austenite also, as is seen -4, -3, -2, -1. These are actually negative elastic strain, that is nothing but elastic strain in the other way, and this is plus on the B side. So, in order to keep these two planes E, F, G, I, J and G, H, L, K intact, there needs to be elastic distortion in the original parent phase, and that is required, otherwise these planes cannot be kept undistorted, and these two planes are known as habit plane, that is why. Now, this is only possible, this kind of situation is possible once if you look at it in detailed manner, this is only possible once you have a shear. Okay, that is what is told in this book. This is only possible when you have a simple shear strain. These invariant planes which are kept there, what I call habit planes, are only possible when there is a simple shear strain involved, where the direction of the movement is parallel to the reference plane. Okay, reference plane is here is basically these two planes which are habit planes. So, the direction of the movements of the atoms, that is even seen there also. See, if you look at the orientation of the plane E, F, G, H, that is bent in the directions same as the distortion of the crystal. So, that is always happens, that means the plane become plane, distorted plane become even plane, and distorted direction remain direction even in the parent crystal, austenite crystal as well as martensitic crystal, they do not get changed. So, that is only possible when they keep the orientation relationship constant without distorting much. Now, surprisingly, there are a lot of experiments has been done to measure these undistorted habit planes in different type of martensites, and these are listed even in the tables of this book. If you look at it, these planes are irrational planes, like some of the planes have indices given in this book as very 922 to 33 or maybe 225 in the steels actually, or even in non-ferrous atom alloys like in titanium it is 8, 9, 12, HKL I am talking about it, HKL is 8, 9, 12 is a very irrational odd planes. So, these planes actually are remaining undistorted, and that is only possible all when you have a shear like deformations. So, what actually happens is that is what is shown in the next picture which I have shown you earlier. What actually happens is like this: if I have continuous FCC austenite unit cells sitting in a manner atomically, where these white circles or these open circles are actually correspond to iron atoms and the closed black circles are correspond to carbon atoms. What we can do is basically that we can actually constitute an BCT unit cell out of the two FCC unit cells, just like the way it is shown in this picture, and the one which is taken out from the construction is shown here in the picture B. You see CY ratio is actually close to 1.04, that is a very small distortion or very small increase of the C as compared to the BCC unit cell of the corresponding alpha phase. So, that means what? These distortions which are happening can be again represented in terms of atoms. Here these the open circles actually iron atoms sitting on the plane, and this dotted open circle actually are sitting on the below the plane, and obviously the carbon atoms are actually shown as a black or closed circles. As you see here that these positions which were there, the carbon atoms actually move from this position to these positions very easily. So thus the whole distortion requires vertical movement of the carbon atoms. These carbon atoms which I am showing here, these carbon atoms actually move vertically simply by application of the shear force like that, like in this way, and they cause the distortion in the magnetic plates. So that is the basically idea. Now if you do this kind of distortion, you generate strain, a lot of strain, and this strain can only be accommodated simply by creating twins. That also can be seen in the simple picture. Suppose if I take a simple undistorted lattice that is shown as A, and then started giving a shear strain, this is given a shear strain, so one has bent, one part of the crystal has become this bent with respect to the other, and again if you want to create invariant planes which will remain invariant in terms with respect to the matrix, then what is required is to give a slight distortion like that. You see, this is a slight plastic distortion given, so atomic planes do get moved, and subsequently these planes will be arranged analytically favorably like that, and this will lead to twin formation. That is very evident in picture from CDE. So thus twins in the magnetic plates are actually because of these heavy plastic distortion which is there required to keep these habit planes intact. That is why this is the shear process leading to that, leads to twins in the magnetites. I hope this is clear and evident from this picture. Details are actually there in the book chapter 10, and this will give you much detailed analogy of the how things are actually done. So martensites actually are, because of the strain, martensites are very hard as you see, and because you have a lot of plastic strain involved, they are brittle, because it has already been it has already accumulated a lot of strain. Now if you want to deform them little bit, it will simply crack or break into pieces, and that is why martensites even in non-ferrous alloys also cannot be used directly except in nickel titanium alloys where martensitic transformation is used for safe memory. So most of the cases martensites needs to be treated separately, because brittleness that will not allow martensites to be directly used in the applications, but they are extremely hard. So that means wear resistance wise they are good, and so it can be applied for many applications. In fact, in many auto industries they use martensitic plates where there is rotating or movement parts which are actually in relative movement to each other are present, and this is mainly leads to wear and tear of the components. So therefore hardness can be used as a means to reduce the wear and improve its resistance for such a kind of wear and tear that is there. Now so therefore we have seen all different kinds of transformations in the steels, like you have seen transformations because of the simple cooling from the austenite leading to pearlite. We have seen transformation leading to quenching, leading to martensites, and we have seen transformations which can lead to bainite formation. Pearlite is a purely diffusional transformations, martensites is obviously diffusionless transformations where shear induced, and there is no what is called temperature dependence is there as far as transformation is concerned. It's only the sample needs to be quenched to bypass the pearlitic transformations. On the other, bainitic transformation is a combination of both this diffusion as well as shear. It is still doubtable, but it can be said that both these features are present in bainitic transformations. Now question is that if we know that steel undergoes all these kinds of transformations from the austenite when it is cooled differently, then can you study the kinetics of the phase transformations and use these results for a means to get some information regarding their transformation. That is what is done in using a TTT curves, okay, that is what I will use. So TTT curves, first of all let us discuss how these TTT curves actually determine. As you know, any diffusional transformation has a time dependence, because diffusion needs time. So when austenite transforms to pearlite, carbon gets partitioned between ferrite and the cementite. So that requires a diffusion. So, what is done? Obviously transformation rate depends on nucleation rate, also growth rate, and even it depends on the overlap of the diffusion fields of the product phase and the parent phase. Not only that, it also depends on the impingement of these phases. So, when they are going together, because they are going separately, so they do not know each other. So, they start impinging each other, then their growth will be hampered. So, all these factors in totality determines the basically transformation kinetics, but important aspect is the nucleation. As you see here, so therefore, if I measure the fraction transformation as a function of the time, it will look like such a kind of curve. Okay, it will look like a S-shaped curve. Obviously, the transformation at a temperature, any temperature will start after a certain time. That is indeed the case for diffusion transformations, because it needs some time to start the transformation, because diffusion requires time, that is why actually, that is the main reason. And this time is shown here at T2 and T1, these two temperatures. This time is known as incubation time, the time after which the transformation actually begins. Once the transformation begins, it increases initially slowly and then increases fast, and finally reaches the maximum value close to fraction transformation 1. So, this curve actually looks like a typical S-shaped curve. Now, one can do it at different temperatures, you can do it at T1 and T2 or even at any temperatures. Okay. So, obviously at T1 the transformation starts at this temperature. You see here the curve has started at this temperature and transformation finishes at this time. The transformation has started at a time here. So, I can draw a line like this vertical line, and this corresponds to my 1% transformation. That means only 1% of the parent phase has been transformed to a product phase. Similarly, this point corresponds to 99% transformation. So, if I draw a vertical line, I can go into 99% transformations. At T2 again same thing can be done. This is T2 transformation rate is basically fast, because you see the time required is much lower than T1. So, 1% corresponds to these, 99% corresponds to that. So, in this way I can actually determine these S curves at all different temperatures, starting with T1 or even above T1 a little bit to down to about much lower temperatures from these positions. So, once you have sufficient number of data, then we can plot a time versus temperature plot, and we can make these percentage transformations as a curve to be shown. As you know, this was fraction transformation versus time. Now, we are actually changing from these to temperature versus time. So, that is why the curve nature gets changed, it becomes a C curve, and I have discussed you to in the last some class before why it becomes C curve. So, basically it looks like a C. The transformation is very slow at higher temperatures, it reaches a maximum value and it can get slowed down. So, by this way we can actually generate 1%, 50%, 70% or 99% transform curves, and these curves are actually known as TTT curves in the literature. The TTT curves actually tells you that what are the different transformations can happen when you cool the steel differently. That is what will be shown in the next plot. So, I hope you understand. Okay, then the next curve is also to let you know how these things are done. Again, one can actually do it in an intelligent way. As you see here, this is fraction transformation, what is known as x, okay, versus time, and you can actually see here at time theta n and at time theta n plus delta t, we can actually determine the percentage transformations differently. This is again a S curve, here also S curve. So, one can determine different percentage of transformations and then we can bring it there, that is possible. So, how we can use this TTT curve? That is what is shown at here, and this is basically one of the measured TTT curves. Okay, as you see here, this is the above which oscillate is stable, below which oscillate is metastable, and these are the two curves at 1% and 99% transformations. A typical TTT curve for 1080 steel or eutectoid steel is basically shown here. And as you see here, these are the two curves which I just shown you. But as you know, Martensite transformation does not depend on time, it is basically a thermal transformation, it depends on the temperature you quench. So, if you quench from the high temperature to 200 degrees Celsius temperature, certain fraction of martensite will immediately form. That is, certain fraction of the austenite will immediately transform to martensite. But if you cool it down to close to 100 degrees Celsius temperature, more fraction will be transformed to austenite to martensites. So this is just depends on the temperature to which it is quenched, and if it is quenched even 0 degrees Celsius temperature, it will transform more. So slowly we can change the transformation fraction of transform product from the parent austenitic phase by quenching at different temperatures. Time has no role to play here, because transformation, as I told you, happens at the speed of sound. That's 10 to the power 7 or 10 to the power 6 actually meter per second. So that's quite high. So at that rate, this has no temperature, time has no effect. That's why these transformation lines are shown as a horizontal lines. It's a flat line at a particular temperature, time has no effect. So only the diffusion transformations, that is perlite and also banites, can be controlled or can be shown by such a kind of C curves. Now how we can use it? As you see, first thing you should note is that A1 temperature, which is basically the temperature corresponding to eutectoid temperature, that is 727 degrees Celsius. Above this temperature, austenite is stable for the eutectoid steel, correct. Only below this transformation temperature, austenite can undergo certain kind of a transformation and leads to different products depending on the cooling rate. So if I cool it slowly, that's shown by this C, curve C you see here, this is sorry, the curve, this one, the curve one which is shown here, is a very slow cooling. Then it will lead to formation of coarse perlite, and coarse perlite means, it will lead to formation of perlite first of all, and coarse means internal lamellar spacing will be very high. That is what is the meaning of the coarse perlite. That is not understandable. Why? Because the driving force, when you cool down from the austenite temperature A1 temperature to, let us say, about 650 degrees Celsius temperature, driving force is low, works under cooling is low. As the driving force is low, therefore the transformation rate is also slow. And not only that, diffusion is very fast here because it is high temperature. So because of that, the perlitic thick diameter internal spacing will be large. That is why it is called a coarse perlite. It has a very low hardness, RC corresponding to the C scale in the Rockwell hardness, and that is very high low, that is about 15. And then if you cool it little bit faster, that is the second, so as the second line you see here, this perlite will also form, but this will be fine perlite. Why? Because you are cooling faster. So if you cool faster and temperature reaches is also low, about below 600 Celsius temperature, driving force increases compared to the previous one, and as well also the time given is small. So therefore diffusion length scale also becomes shorter, and that is why this leads to reduction of the interlamellar spacing in the perlite, and that leads to formation of fine perlite, and hardness can be jumped up from 15 to about 40 in the Rockwell C scale. That is actually good. So therefore if you want to change the hardness of perlite, you can cool it faster, but not very fast obviously. So inside that you see this is written A plus P, P corresponds to perlite, A corresponds to austenite which has not yet been transformed fully. Now in order to form benite, we know that the heat treatment cycle, we have to quench so that perlitic transformation does not happen. So that means what? That means you see this is the nose of this C curve. So once you cross the nose of the C curve, austenite will automatically transform to perlite. So the only way to avoid the formation of perlite is to bypass this nose. Therefore you should know the critical cooling rate to bypass the nose of the austenite to perlite transformation. That is not difficult. Once you have the diagram, you can draw a line from the A1 temperature to, which will be tangent to this C curve, and the tangent slope will provide you the critical cooling rate. So therefore to bypass the perlite formation, the cooling rate must be higher than this critical cooling rate. So once the cooling rate is higher and the austenite will not transform to perlite, then if we keep it at about 450 degrees Celsius temperature, basically from 350 to 450 degrees Celsius temperature for a long time, it is about, let us say, about 10 to the power 5 or 4 5 seconds, that is quite large time, and then it will lead to formation of the upper benite or lower benite depending on the temperature. Upper benite will form about 450 degrees Celsius temperature, lower benite forms at about 350 to 280 to 350 degrees Celsius temperature. So basically this tells us that the benitic morphology can be changed depending on the holding temperature. Whatever is the fact, whatever be the holding temperature, the sample needs to be cooled rapidly enough to bypass the nose of these austenite to perlite transformations. Another important aspect of that, suppose if you cool it directly from the austenite temperature rapidly to the martensitic start temperature MS, then it will lead to formation of martensites. Obviously, this will lead to bypass of the both austenite to perlite and austenite to bennetic transformations, and this is shown in this picture. As you see here clearly that the martensitic start temperature is shown here, this actually tells you the start of martensitic transformation temperature, below which martensites will form. And once it is cooled below the temperature, martensites will automatically form. It does not depend on time at all, that is why I told you. So, the next lecture we will discuss a little bit more about it, so that you understand also martensitic transformations and also the related issues.